I hope all of you are doing well and safe. So the contents for this talk are outcome of research work done with my master students, Rohit Joshi and Manish Rao. Manish Rao graduated with an MTech from IIT Delhi recently, whereas Rohit is still working towards his MSR degree. And the majority of results that I would be presenting today are his contributions. So to set the context into this talk, I think nowadays on a regular basis, we come across news articles on security threats on various systems around us. This could be a central database. It could be critical infrastructure such as power grid or urban transportation system, and even enterprise networks. For example, Garmin recently came to news because of this. So these revelations sort of tell us that it is imperative to not just look at designing a system from a functional viewpoint, but also be very attentive to vulnerabilities against a wide range of security threats. And then we need to hand in hand come up with countermeasures to mitigate those threats. So in terms of security threats, broadly, security features fall into three classes. One of them is confidentiality, which is basically you design a system to prevent unauthorized access to data of privacy, right? So another aspect is availability. You design the system so that the clients get access to the services. And integrity is you prevent unauthorized access to tampering of data or manipulation of data or messages, right? So these are broadly the security features that are designed. Now, going forward, I think with the number of use cases involving connected devices around us, we can expect a lot of new attack surfaces wherein the attackers could execute new threat models using which they may compromise some of these security features. Now, in this talk, I'm going to talk about focus on only the confidentiality feature. Although I'm not going to talk about availability and integrity, although they are equally important in security. Right. So in order to provide confidentiality, traditionally what do we do is we fall back on crypto primitives whenever we are communicating data from one end to another. For example, we could either use a symmetric key encryption method or an asymmetric method, which is basically a public key encryption technique. So what happens, as shown at the top, in the top is, these two communicating parties, they have access to a common key, it's a shared key, using which they would encrypt their messages and then transmit, because of which, the receiver would be able to recover the message by decrypting it, whereas a third-party eavesdropper would not be able to recover the message because the third party doesn't possess the key. On a similar lines, in the public key encryption, as depicted at the bottom here, the receiver would carefully generate a pair of keys. One is private and the other one is public. So the public version would be provided to all the potential transmitters. And these transmitters who would want to keep their messages confidential would encrypt their messages using those public keys. And then, once the message is received, the receiver would decrypt it using the private key, right? So these are broadly two types of encryption mechanisms that are used to have confidentiality feature, right? So, and the usage of these techniques really depend on the application. And as far as, let's say, communication with the base station is concerned, for example, in a cellular network where a subscriber device would like to talk to a base station, in that case, both these nodes, they possess some common information, for example, pre-shared identity in the form of a SIM. And usually what happens is this is used as a route, for the process of authentication and key derivation and so on, right? So that gets much easier. Whereas there are other applications, for example, in device-to-device communication, wherein the communicating parties need not have access to any pre-shared identities, and in which case they would need to execute another round of algorithm to exchange the keys between them. So once they generate a key between them, then they can subsequently use it to apply crypto primitives and hence provide the confidentiality feature. right? So talking about the confidentiality feature with crypto primitives, and as we see that, in a D2D setting, key exchange mechanism is important. Now let's look at a traditional, again, crypto primitive technique, which is used by the communicating parties to generate the keys. So for the purpose of description, let's consider good old players, Alice and Bob, who would like to exchange keys between them. And then obviously we have the third party eavesdropper, who is keen on listening to the conversation between the two, right? So let's go through briefly the algorithm behind what's known as a Diffie-Hellman based key exchange. So what happens here is Alice is going to pick up a random number A. And then both of them agree upon a common base, let's call it G. And then Alice would transmit G power A to Bob. And similarly, Bob would pick a random number B, and then he would also transmit G power B to Alice. Now, what Alice does is, by receiving G power B from Bob, she would raise it to the power A and then get hold of G power AB. Similarly, Bob would also do the same thing on his side, and then he would get G power AB, right? So what they have done in the process is that they have a common number between them, which is G power AB. Now, potentially, they can use this as a common key so that, they could use it for applying their crypto primitives, okay? Now, what happens at the side of Eve is Eve can view G power A in the public broadcast. She can also view G power B, and also she knows G. But then, despite knowing G power A and G power B, it is not easy for Eve to recover G power AB. Well, if you look at it as let's say if A, B, and G are all real numbers, if you look at it, maybe it looks possible, right? Because if you have G power A at Eve, then maybe she can apply log of this number to base G and then get hold of A, right? Similarly, she can also get hold of B like that. But, this is possible as long as they're working in a real space, set of all real numbers. Whereas when this Diffie-Hellman based key exchange mechanisms get implemented, the numbers A, B, and G, they don't come from a real line. They come from a finite alphabet of sufficiently large size, which has some algebraic property. Maybe it's a group, or it could be a ring or a field. And as a result, even if Eve get holds of G power A, it cannot apply any known log and logarithmic techniques here. So the only option with Eve is to sort of exhaustively try all possible elements of this alphabet in order to match the G power A. So this is usually what is known as the discrete logarithmic problem. And then if the alphabet size is extremely large, then this is computationally challenging for Eve to get hold of A and B, and therefore G power AB remains a secret. So this is one of the straightforward techniques which could be implemented at the higher layer of protocol stack. And once they have the key, they can use it to apply their crypto primitives. Now, what happens is, other than Diffie-Hellman key exchange or thinking about crypto primitives for confidentiality, we also have a lot of other techniques which have attempted to provide confidentiality. So to take a step back and look at the big picture, what we have on one hand, we have crypto primitives, which would need secret keys. On the other hand, in the recent past, the Information Theory Society or even the Communication Society have tried in what is known as physical layer security. So basically, the idea is to somehow provide confidentiality to the legitimate users in a keyless fashion, meaning somehow what they do is the technique exploits the difference in the channel quality between Alice and Bob and Alice and the eavesdropper, and then somehow use this difference in the channel quality to embed the information confidentially, right? So these are essentially two different classes of it. And coming to the topic of interest, which is a subject matter, this is basically physical layer key generation. Basically, we are looking at new methods to generate keys between devices so that they could be used for confidentiality purposes. Now, as shown here in this particular picture, we have actually identified physical layer key generation in the intersection of these two classical types of methods. And the reason is, the whole idea of physical layer key generation is to extract secret keys using the randomness in the wireless channel. And that means we are making use of the physical layer characteristics, and therefore they fall under the physical layer security bin. And similarly, once the key is somehow generated, either we could use it at the physical layer for an additional layer of encryption or something like that, or what we could do is we could perhaps push this digital key through the protocol stack to the higher layer, and then a crypto primitive block could make use of these secret bits to encrypt the messages. And therefore, because of this common points, we think that the whole idea of physical layer key generation sits in the intersection between the two. Right. So I think with that background, I think we are now ready to move into the technical contents of this particular talk. So here is an outline of what I'm going to present today. Briefly, I'm going to introduce the basics of physical layer key generation. And then we are going to look at a generalization of it. That's what is known as a group secret key generation. I'm going to talk about it in detail. And then the majority of the time, we are going to look at a very specific case of group key generation. I'm going to call it the curious case of a 3-node network. So basically, a 3-node network is a very simple example of a multi-user setting, because it's not just 2-user, it is one more than that. And then this would be used to understand the challenges involved in generating a group secret key using the physical layer techniques. So we are going to go each one of these one by one. Okay, so with physical layer key generation, as mentioned earlier, we have two participating nodes, Alice and Bob. They would like to harvest a secret key by using the randomness available in the wireless channel between them. Right, so they're not going to fall back on the Diffie-Hellman based key exchange. They're going to do something new. So this is exploration. So what they do is in this idea, Alice and Bob they are going to transmit to each other pilot symbols. So these are called probing symbols. These are known symbols to each other, and as a result of which they are going to observe their channel between each other, right? And then if they keep doing this for some time, they will be able to sort of visualize or have witnessed the variations in the temporal randomness offered by the wireless channel, and that is one of the important steps here, because just with the process of sharing pilot symbols within a given time slot in what is called as a time division duplex manner, they can actually witness a source of randomness over time, and then eventually that could be used to harvest a secret key. Now, what happens at the side of an eavesdropper with Eve is that because of her geographical location, even if Eve is able to overhear or hear the pilot symbols from Alice and Bob, the small scale fading effects at Eve would be uncorrelated or statistically independent of the main channel. And as a result, even if Eve mimics the operations that are performed by Alice and Bob, then she would end up with a bit sequence which is going to be totally different from what these two agree upon, right? So that's the whole idea of physical layer key generation. Now, there are two fundamental reasons why this potentially works. So one of them is the rich scattering environment in a wireless channel, basically the multipath fading, because of which the channel variations that they witness is random. Especially, it is desired to have randomness of large variations, so that this would lead to a very high entropy random variable. Right? So that is one of the reasons. And the other reason is what is very well known as reciprocity. And what this means is, if these two nodes exchange their pilots within what is called as the coherence block, meaning imagine the environment around them is almost the same during this process, in which case what happens is the channel variations observed at one node is going to be highly correlated with observations at the other node. And this, in essence, is going to give them a common source of randomness, which is accessible as well as secure. And once this job is done, the rest of the process is fairly simple. All that they need to do is somehow convert these samples into bits by some type of quantization. And once they do that, they get a hold of sequence of bits, and somehow they need to arrive at a consensus on which bits are the same polarity and so on. And then finally they would end up with a long string of bits, and once they decide that they're identical, then they could subsequently use it to encrypt using the traditional crypto primitives. So in the process, they will have to go through what is known as a consensus algorithm. Now, one such popular algorithm that we usually come across is what is known as the use of guard bands, right? So here is a picture wherein we have plotted the random samples experienced by both the nodes in the case of two users, node 1 and node 2, which are Alice and Bob. Now, guard bands play an important role here in order to mitigate imperfect reciprocity and additive noise at their own side, because these random samples are not identical; they're only correlated, right? Now, with the use of guard bands, what they do is they are going to divide this entire zone into two levels, which is the simplest case of generating a bit out of a sample, and then they just don't mark a single boundary. What they do is this boundary is also relatively thick. And the reason is that, if they make it thick, what happens is when we have a sample that lies inside the guard band, they're going to discard it. Because, potentially the sample in the guard band might have come from the adjacent region. And, this could eventually lead to an error between the bit strings that both of them possess, right? So what we do is, if we think that if the noise levels between the two users is huge, then we try to increase the guard band, the width of the guard band, in which case, if the guard band is large, then the probability that, the sample at one user appears as sample at the other user in the different region is very low, because the sample would need to cross this huge guard band, right? So that's the main idea. But on the other hand, by increasing this guard band, we are also going to lose out on the samples, because once the samples lie in the guard band, then we wouldn't be using them for extracting the key. So there is some amount of tension here, in the sense, if you want to reduce the error between the bits that are at the two ends, then you will have to increase the guard band, which means the total number of samples in consensus would be low, and this in turn would affect what is known as secret key rate, which is basically the number of bits that you could extract in a given amount of time. Right? So once this process is executed, essentially each user is going to identify their samples which are out of these guard bands, and then they are just going to share these index values. And the other user is also going to share his index values. And finally, these two are going to only look at their common indices, and then they are going to get the bit sequence out of it, right? So they are not going to reveal the polarity of the samples on those on those indices, but they're only going to share the index values, right? So that is how the confidentiality is achieved, right? So two-user secret key generation through physical layer has been fairly well studied. There have been results in terms of fundamental limits, information theoretically. There have been prototypes and experimental demonstrations, and researchers have also looked at new consensus algorithms on various platforms. It could be multiple antenna platforms, or it could be fiber optical networks, or OFDM, and so on and so forth. So as far as two-user case is concerned, we think it is fairly well understood. Now, moving on to the topic of interest. So what we are interested is in the topic of group secret key generation. So the application here is that, we don't have just two users. We have more than two, let's say arbitrary n users. Okay, they form a group with some topology, right? Some of them may be connected to some of them, and some of them maybe not, and so on and so forth. But then, loosely speaking, it's a group of several users. and they would like to harvest the secret key from the physical layer. Okay, so the motivation is still the same. They would like to harvest the physical layer key, right? And typical applications to this involve, maybe they all would want to decode a broadcast information from one of them, or maybe let's say they follow a relaying protocol. In the process, they may have to open the packet, modify the packet, decode it, and so on. In which case, they may need to have the key to sort of look at the plain text values and so on. So these are the various applications for group secret key generation. Usually, they can be seen in an ad hoc network scenarios. Now, again, looking at the literature, there are a number of research contributions in this space as well, mostly looking at algorithms for key generation, fundamental limits, and so on. Now, to give you an idea of the challenges of group secret key generation and what exactly it is, I'm going to take a look at this toy case, right? This is the curious case of a very simple 3-node network, okay? So I have two figures here. Let's focus on the left one to start with, okay? So broadly, we can classify group secret key generation into two types. I'm going to call one of them as a pairwise based GSK and the other one as a group consensus based GSK, right? So I'm going to talk about the pairwise based GSK first. That is the figure on the left-hand side. So we have a very simple network of 3 nodes, node 1, node 2, and node 3. And it's a wireless network. Therefore, there is a channel between them. H12 is a channel between node 1 and node 2. H13 is the one between node 1 and node 3. And likewise, H23 is between node 2 and node 3, right? So now these 3 nodes would like to extract a secret key so that it could be used for group broadcast and other things confidentially. Now, one approach to get hold of a secret key is as follows. What they could do is they could piggyback on the simplicity of pairwise key generation. So what it means is no new protocols are required. They just go back to the 2-user case wherein you see node 1 and node 2, they just work like a 2-user key generation case. They exchange their pilot symbols and somehow generate the key K12. Okay, so this K12, let it be a binary key string, which is generated from the physical layer using the common randomness in the channel H12. Right? Similarly, node 1 can also extract the secret key K13. This is from between node 1 and node 3, and this is using the channel variations in H13, right? So again, I want to emphasize here that K12 is obtained using pairwise algorithm, and K13 is obtained using pairwise with a different node. So once K12 and K13 are retrieved, node 1 can act as a facilitator by doing a very simple job. What it does is it could just XOR these 2 bit strings and then broadcast it to both node 2 and node 3, right? And then upon this, what node 2 and node 3 can do is they can apply successive cancellation at the digital level, and then they can get hold of the key. For example, node 2 doesn't have to do anything here because node 2 already has K12. Now node 3 can receive the broadcast message, and then it can recover K12 because fundamentally node 3 had no access to K12, right? So it could actually get it because of the broadcast, right? So this is very simple. There are no new algorithms required. They all piggyback on the popularity of the pairwise key generation, and it's also fairly simple, right? That's one side. Now let's look at the right-hand picture. Now this is slightly different. The approach itself is different because what they do is what is called as a group consensus-based group secret key generation. What it means is, in this particular model, we are not willing to give the responsibility of key generation to one of the nodes. Okay, so we don't want to rely on just one node to do all the job. What they do is all of us are going to play the same role. So, but somebody needs to help us to witness a common source of randomness, right? Because what happens is H12 is only seen between node 1 and node 2 in the process of, let's say, pilot probing. Similarly, H13 is only seen between these two. But then if you look at it, node 3 and node 2, they cannot really have a common subset here, right? Because unless they have a common subset, they don't have a common randomness. And if they don't have a common randomness, how can they generate a key out of it, right? So in this particular model, what node 1 does is something very similar to the first scheme, but it doesn't extract the key. What it does is it somehow learns H12 and H13 at the raw level, and then it's going to broadcast some function of these two. Okay, so that once this is broadcast, this node 3 is going to recover H12 using the received broadcast symbol, right? So, and then what happens is node 3 gets hold of H12, some noisy version of it. Node 1 and node 2 already have access to H12, and with this, what we have done is we have sort of forced a level playing field among them. Now, all of them now have a source of common randomness among them, right? Now, what is the main difference between this approach and the previous approach? So as I mentioned, we don't really want to give the responsibility of generating the keys to one node, right? So for somebody who has worked on the ideas of distributed ledgers with blockchain technologies, this idea is reminiscent of that. Basically what they say is all the nodes would like to actually look at the randomness, okay, and then we would like to execute what is known as a group consensus algorithm, right? So the consensus is not going to be only pairwise like what happened here, but it's going to be a group one in the sense, node 2 would broadcast its index values and the others would listen and so on and so forth, right? So we have recently shown that adopting this second scheme of operations, some of the insider attacks, if it happens, can be mitigated using the group consensus, and that's basically what the philosophy of distributed ledger, right? So this is something very similar to that. Now, while we take this particular approach, the question actually is that this is very generic. What we are saying here is we are going to broadcast some function of H12 and H13, but then we will have to really carefully ask, as in which function to use, whether it's going to give us common source of randomness with large entropy, whether is it going to leak any information to the eavesdropper and so on and so forth, right? So for the rest of the talk, we are going to talk about this decentralized setting because of the motivations that was just explained.
So Harshan, a question.
Yeah.
In the previous slide, the left-hand side protocol, can you tell us what the shared secret now? Is it just K12 or is it the pair K12 and K13?
It's just K12. If they decide to use both K12 and K13, then that would no longer be confidential.
Okay. Thank you.
Okay. So that's basically, if K12 is the secret bit, and then if K13 is also uniformly distributed, and then K13 is not known to the eavesdropper, that's basically a binary symmetric channel with probability 0.5, right? So, and therefore the leakage is forbidden.
Harshan, one more question.
Yeah.
In the previous slide, you had this insider attacks, right?
Yeah.
So is it like you assume that some of the nodes are trustworthy, and then those kind of things can be handled by this group consensus?
Correct. So that's precisely the point. If you give all the responsibilities to one of the nodes in the network, then sort of we are relying on that node, and if that node turns rogue, then it's out of control. So if that node turns malicious, then it can be shown that using group consensus method, we can to some extent try to mitigate those activities.
Okay, thank you.
So that essentially forms the motivation to look at the decentralized setting. Now, definitely because of that motivation, the process is going to be more complex compared to the former scheme, because the former scheme just relied on the two-user key generation, which was fairly straightforward, right? So in order to study the decentralized setting, let's formally look at this network model. We had three, but now we have also roped in the fourth node, which is the eavesdropper. This basically to understand the leakage effects of this particular protocol, right? So the setting is very similar, very familiar to anybody who has worked on wireless networks. Between any two nodes, we have a wireless channel, and the small scale fading between them is appropriately represented by the subscripts. right? And then because these nodes, they share the time in an orthogonal manner, some sort of a TDD protocol is implemented, and therefore, if all these operations take place within a given coherence block, we can expect that each of these channels exhibit pairwise reciprocity, right? So that is also one of the assumptions, right? So now we have to focus on multiple things. Number one, how do these nodes have access to a common source of randomness? Okay, and once somehow that is achieved, then we can think about how to really generate secret bits out of it. So it's sort of a two-step problem that we are trying to approach. Okay, now in particular, in order to generate the key, we need common source of randomness. And where do the randomness come from? It has to come from the wireless channel. And then how many wireless channels do we have? In the legitimate sense, we only have 3 of them. One of them is H12, the other one is H13, or the H23, right? So then it's important to decide which one of them we need to go ahead with. And once we decide which one to go ahead, how do we really share this common source of randomness so that all of them are on a level playing field to observe the same, right? Now, in particular, what we want to ask is, how do they share the common randomness? With practical constraints. That means these algorithms must be implementable on a state-of-the-art radio devices, right? And then the protocol must be such that the eavesdropper who is keenly watching the proceedings must not get anything related to the key. And finally, the protocol must be such that the total number of bits that are generated within a given amount of time has to be maximized, right? So we are going to look at these 3 constraints and then see how we can really answer them. Now, think about it. How can I really achieve all these nodes to observe the common source of randomness? So I would request you to look at these pictures from the left top in a clockwise direction, which means we are going to look at this first, second, third, and fourth. Okay, so in the first 3 figures in the clockwise direction, basically every node is broadcasting a pilot. Okay, and the other nodes are all silent. And because of which, the receiving nodes, what they can do is they can learn the channels connected to the transmitting nodes. For example, node 2 can learn this channel H12, node 3 can learn H23, and so on. Similarly, when in the next time slot, when the facilitator or when node 1 transmits the pilot, the other nodes learn their channels and so on. And then in this process, what happens is, if you look at the end of the third phase, they would have learned their respective channels, but still at this point in time, their intersection is non-empty. So rather, their intersection is empty, right? And then that doesn't serve the purpose because they would need common randomness. So in order to fill the gap, one of the simplest ideas is this node 1. You recall we had thought about a function f of h12, h13, right? The simplest of such functions is, let's say, linear combination of these 2. And this is basically motivated by physical layer network coding ideas that have been popular so far, right? So if this node, because of its knowledge of H12 and H13 in the previous phases, it quickly learns them and broadcasts the sum. And then, what happens is node 2, while receiving it, can actually learn H13, which it did not have any exposure to. And similarly, node 3 can also learn about H12, which also did not have any exposure to, right? So this is with the 4th round of the protocol. Now they have, in some sense, are able to witness randomness, which are correlated among all 3 of them. Okay. Now, just to look at the same procedure in a slightly different picture, you have to see this from the top to bottom, right? So what happens is, in the first phase here in this parallel line, they are all going to estimate their channels using the pilots. And naturally, as you can see here, there is no intersection between them. So they need to do something more. So what the node 1 does is it broadcasts, and then the other nodes recover. And then finally, they end up with a pair. And all of them look identical here. That's mostly because we are, for the explanation purposes, we are only looking at the no noise case. Okay. Now, whatever it is, the good news is that now H12 and H13 are now available at all the 3 nodes, which was not the case with just probing signals, right? Now, all is not well here because there are constraints. There are practical constraints. And what it means is, what are these H12 and H13? H12, H13 are the samples coming out of the ADC of the receiver, right? And typically ADC has about 14 to 15 bits, and these are all high precision numbers, right? And then, broadcasting these numbers as it is not practically possible, because usually any wireless device broadcasts using finite constellation. It could be, let's say, a 16 QAM or a 256 QAM, or up to 1024 QAM, or whatever it is. I mean, even then, if we want to even go to 1024 QAM, there is still a mismatch in the precision of ADC and the size of the constellation. And what this means is that once you have a H12 and a H13, even if you want to send this to the other nodes, you will have to make use of multiple channel uses because of the precision levels, right? And then that's going to be a communication overhead, right? So we are not going to do that because of the overhead. So what we want to propose is that, let these ADC bits be large, 14 to 16 bits. But what I'm going to do is I'm going to directly quantize these complex numbers, high precision ones, onto my constellations, because anyway, these are going to be my transmission symbols, okay? And then once I quantize them, I'm going to use the quantized version, right? So all I'm going to do is I have a constellation here. I'm going to get a random sample from the distribution. Let's say if it is Raleigh, then these numbers are going to be Gaussian. And then I'm going to quantize it to the nearest one. And then the symbol that would be sent by the node 1 is one of those points in the QAM constellation, okay? And then, that's one of the ways to make this practical, right? And then, so what happens to the protocol then is everything else remains the same. But if you look at this broadcast phase, we are not going to send H12 and H13 as it is, sum, but we would quantize the sum into the QAM constellation. And because of this quantization error Z creeps in, right? And then because of this influences a lot of other things. However, the operations don't change, but in the end, what happens is in the last block, if you see here, they have recovered the common randomness, but then there is some amount of asymmetry in their noise levels, because one node looks at the random samples as they are with very high precision, whereas the other samples only are able to recover the quantized version. So this asymmetry is only going to result in a suboptimal performance, and really we don't want to take this as a way forward, right? Now, in order to solve the concerns raised in the previous slide, a simple idea, which is a generalized version of the previous one, is I'm not going to quantize the sum of the complex random variables. What I'm going to do is I'm going to individually quantize them, right? So H12, I'm going to quantize it to the QAM point, and then I'm going to get Z1, which is the quantization error associated with H12. Likewise, Z2 would be the quantization error associated with H13. And then once we quantize these two individually, only then I'm going to add these two numbers. Okay, and then the rest of the process is same, but because of this particular operation, we can actually introduce minor modifications in the protocol and then come to a point to the last phase here, wherein, as you can see, all the nodes now have access to the common randomness, which are essentially of the same level in terms of the noise, right? So that is a very nice thing to know, because they now have common randomness of the same noise level. Well, everything is good in terms of practicality. However, a quick observation will tell us that if one of the quantized values is the source of common randomness for key generation, and what you see here in the second argument of the mutual information, this is basically the symbol observed at the eavesdropper. And a quick calculation would reveal to us that the mutual information between these two random variables is non-zero, which means that whatever eavesdropper observes is going to be not statistically independent of the source of common randomness, which is not a great news, right? So what it means is, I think there is a typo here, I'm missing in the bracket here. So what it means is, although we try to ensure practicality of sharing the common source of randomness, the leakage is non-zero, and this is one of the crucial yardsticks for the protocol, and therefore this is definitely not the choice to go forward, right? So We fix all these things by this particular solution. What we are going to call this as algebraic symmetrically quantized group key generation. Okay, so what is the change? Almost all the things are same. The only difference is in the second stage here. Now we will continue to quantize these channel realizations individually, but the only difference is we are not going to add them as two real numbers. Okay, instead what we will do is we are going to view these symbols as elements of some algebraic structure. It could be a group or a ring or a field. And once we give that viewpoint, then what happens is the addition operation that is performed by node 1 is going to be over that algebraic object. And what we can show is that this is going to give us a lot of benefits, right? So this is going to be an algebraic addition appropriately, and that is what is broadcast. And the other two nodes are also aware of the usage of these algebraic objects. They would appropriately use these objects and then also recover what was not known to them. And then finally, they are going to end up with random variables that are correlated, right? So as you see in the last phase of this protocol, all of them have the same set of random variables. So that's a great news. So the only difference between this scheme and the previous scheme is that instead of adding QAM points as they are as real numbers, we are now adding them as algebraic objects in order to ensure the confidentiality property. And that's just easier said than done, but the implementation of this particular idea is fairly involved. And the reason is that let's focus on the picture on the left here, right? Now, what is this? We are at the phase of quantizing this channel H12 to the QAM point. Now, I would not like to quantize this to the QAM point. One of the main reasons is that, see, the QAM point constellations are all uniformly spaced, right? And then if these H12, H13 are all sort of Gaussian distributed because of the Rayleigh fading characteristics, if you look at the probability mass function induced on these discrete values, they are not going to be uniform, right? And that means it's asymmetric. It's going to have a large mass points in the center and then the minor mass points on the side, and then that is not really congenial for key generation because the underlying randomness itself is not uniform, right? So what we want to do is, at the phase of quantization, we don't want to use a QAM constellation. Instead, we would like to design a constellation which looks something like this, and that forcefully ensures that the quantized samples are uniformly distributed. And this can be done if we have the knowledge of the distribution. That's point number one. Point number two is, once these symbols are obtained, then we talked about algebraic operations, right? What we could do, for example, here is we could map these symbols into these 16 points. This is what? This is essentially Z4 of I. Basically, it is Z4 on each axis. And then, we could add them as modulo 4. And then what happens is, this is going to be an element in this particular ring. This is going to be an element in the ring. And when we add these two elements, this is not going to go out of the box because it's not regular addition. Whereas, instead it is going to retain inside the box. And once we have this element retained here, we could apply an inverse map because essentially these are all one-to-one mappings. Now, the last thing, this is fine. This constellation is fine. But then what happens is the facilitator also has to broadcast, and the broadcast symbol has to be decoded and then recovered by the other nodes. And as you can see, we cannot really use this constellation because it's not energy efficient. We cannot use this constellation because the minimum distance properties of this is not great. So what we have to do is, once we really get a result of the sum, we have to again map it to the regular QAM constellation of the same size, and then only broadcast it, right? So if you go back to the previous picture, it looks very simple, but then if you really have to implement it, you will have to take or seek the help of various constellations which would do their appropriate tasks. Okay, and overall, what does it look like? Basically, this network of nodes would be using a lot of one-to-one mappings among these three constellations in such a way that they end up with a random variable which is uniformly distributed at their side, and also at the same time make sure that when node 3 recovers the unseen random variable that is of preferably lower, has low error compared to the other nodes. Okay, so that's the brief overall idea. And then because of the algebraic nature, it is straightforward to prove that now if the eavesdropper listens to the conversation among them, it is very easy to prove that nothing leaks to the eavesdropper. Essentially, the mutual information between the observed variable and the random variable used to extract the key is zero. I'm not getting into the proof of it, but that's basically the takeaway point, right? So all these explanations. Yeah.
Hi, Shashank. Sorry for the interruption. So there's one more step here, right? Because in the second stage, when you broadcast the sum of the two QAM points, so there is a non-negligible probability of error, right? That node 2 and node 3 decode some incorrect.
That's right. That's right. So especially, sorry.
So how do you make that small? Do you add another layer of encoding?
Yeah. So that's a great question. So as of now, if we go ahead with this scheme, this is something that we will have to live with. And I'm going to talk about it in the next slide, as I was about to do that. So in the noiseless case, all seem well because there are no errors. But then in the noisy case, this is what we are going to have, as exactly pointed out by you. Okay. So what happens is, because of noise, now all of them have now recovered samples that are fairly random. Now they all belong to this discrete constellation. But then if you look at it, let's focus on the samples coming in from H12. Now H12 is now with everybody, but it's just that the version which is with node 2 and node 3, that has got affected only by maybe an estimation error or a reciprocity error. That's all. So the level of noise at these two nodes with respect to H12 is only that much. Whereas if you look at node 3 and its corresponding sample from H12, now this H12 is the recovered version from the broadcasting. And then because of the potential error in decoding, now the noise level at node 3 is definitely degraded compared to the noise levels at node 1 and node 2. Right now, we haven't seen at really how to improve these noise levels at this stage, especially given that there is no room for applying any coding across time or space, because essentially all these operations are going to happen quickly in the protocol with just about 4 channel users, right? So if we constrain ourselves to these 4 channel users, there is not much room apart from really ensuring that the minimum distance properties of the two-dimensional constellation is maximized. Maybe instead of a QAM, at most I could use a hex because of its distance properties, but essentially that's a seal. I can't do more than that unless I am allowed to use additional time slots to code across time or any other dimension. Okay, so just to summarize where we stand at this point in time, we have taken up the decentralized setting as an interesting case for its benefits. And then all that we have done so far is how to share the common randomness among them practically as well as confidentially. Okay, and what lies ahead in this is they all have common randomness now. They're all discrete. They belong to the QAM constellation or any of those 1-1 mapping based constellations. Now the next question is how to synthesize secret bits out of them. So I'm going to talk about this in the next section of the talk. I can actually take questions because this sort of concludes one portion of the contents that I had to deliver.
Harshan, so one question. Is there any comparison or with the Diffie-Hellman itself?
Yeah, so that's an interesting question. What has been shown is, especially when key exchange methods are implemented on resource-constrained devices, executing a Diffie-Hellman algorithm is going to be computationally expensive. And while there are no issues like quantization and other things, what we think is that, you know, in the Diffie-Hellman, even there they would need to work on an underlying finite field, because the exponent and the base come from an underlying field. And then, you know, the process of exponent computation itself is multiplication several times over a corresponding field with the underlying polynomial explanation, right? So implementing that itself is going to be extremely challenging on a resource constrained device. Whereas in contrast, in this setting, all that they are focusing on is exchanging the pilots, right? And with a little bit of decoding and modulation. So that is where we draw a line between these two streams.
Okay, thank you.
So Harshan, Lenka, go ahead.
So is this extendable to any number of users? Okay.
Yeah, I'm going to come to that in the last. Yeah, I'm going to come to that in the last part of that. That is definitely something that we are excited about, because as I mentioned, you know, this is a toy case of the curious case of the 3-node network.
So Harshan, if you have time for one more question.
Okay.
So I'm just thinking about your last comment. So I think your comment was that, let's say we take only this particular channel H12, and
Okay.
and then I think our understanding is that you can extract maybe only so much randomness from it. So I'm just thinking if maybe there are other things to do. So let's say you have the channel H12, but let's say you rotate it a little bit, and then you allow the receivers to quantize. Although there is some correlation now with respect to the quantized quantities, with rotation and without rotation, maybe there is some more information that you can extract.
Sure, that's a good point. Now, if we go with the assumption of circularly symmetric Gaussian random variables, we can as well unfold them into two real random variables, and then you know, you could look at extracting bits out of those amplitude levels. So that would in fact give them twice the number of bits, because you're unfolding the bits into real and quadrature.
Okay. Okay, thank you.
Yeah, Harshan, I guess here in this scene, you're basically limited by how fast the channel evolves, right? Because presumably, if the channel doesn't evolve very fast, then you can only extract a very small number of bits of secret key, right?
That's right. So this has to be a sequence of observations temporally, and within a given coherence block, they perform this protocol, and they all get hold of a realization of a random variable H12, and then there is as much as you can do with this random variable, because because of its dynamic reach. Then you go to the next coherence block, then you're again going to witness another realization, and so on and so forth. So as you grow with time, we are going to accumulate more randomness. But then if you look at the key rate, normalizing it over time, then essentially this amounts to how much of entropy does H12 has to offer.
But does it even need perfect statistical independence, of course, across coherence blocks, and also between the users and the eavesdropper?
Yeah, so it would require perfect statistical independence across coherence blocks if we are looking at what is called as the entropy metric, because once we have the information bits in binary, then we are going to look at it as a string of bits, and then the adjacent bits are going to be statistically independent if the underlying random variables themselves are. So that is extremely important. And as far as statistical independence among the users is concerned, it is indeed required to prove some of the results. But the statistical independence with the eavesdropper is extremely important. That is one of the assumptions made to ensure that confidentiality is assured.
Yeah, and also independence across users is also important because you're broadcasting the sum. So I suppose you will somehow require the sum to be independent of the individual HIJ.
That's right. That's right. So when we go back to pen and a paper and then compute the mutual information with respect to the eavesdropper, then we would need these assumptions to prove that its mutual information is zero. In fact, what we have shown is they will have to be identically distributed. So it's not just independent, they also have to be identical in order to prove the results. But then I'm not sure if we have given a thought on what would happen if they are not identical. Maybe I'll have to come back on that later.
So don't you need uniformity at some point? If it's the points are uniformly distributed across the points that you're transmitting.
Yes.
Transmitting, say, H12 plus H13, then you need H12 and H13 to be uniformly distributed. And
that's correct. And that's the reason we made use of a constellation, which is different for quantization. So what we did there was we packed, so probably I'll go back here. So if you look at the constellation on the left, that is designed to ensure that the discrete samples are uniform because we knew the Gaussian distribution. So what we did was we placed the some of the interior points so close to each other that when you compute the probability mass values on the interior points, it's going to be equal to that of all other points. So inherently, the quantized values seen from H12 and H13 both are uniformly distributed, and therefore, when you compute the sum of these two over the ring, you would induce no leakage.
Harshan, I think there's a question in the chat.
Yeah, could you please read that to me?
Yeah. So any converse result for group secret key generation on?
No, we are not aware of that, especially in the case of decentralized setting. So in fact, we don't even have achievability results. So whatever we are working with is a method to share the randomness. I don't think we can comment on the tightness of the current results that we have.
So here, I mean, assuming that there are no other constraints of computation complexity, or I think there is work literature on secret key generation, right, by Prakash Narayan.
Exactly. Yeah. So you must be referring to his paper in 2004 that they have exploited it. But then, that is definitely one way to look at it from an information theoretic point of view. But then once we start using these practical constraints of modulation size and so on and so forth, we will have to rederive those results which are applicable for finite constellations. So that I'm referring it to as not sure about.
Sure.
Yeah. Shall I proceed?
Yes, Harshan.
Yeah, so I've already taken up 1 hour. I don't know how much time do you think I can go on for some more time?
Harshan, how much more time do you think you need? So we have a formal time limit at 7:30.
Okay.
So if you want to exceed it by 5 or 10 minutes, that's fine with us.
No, I wouldn't want to take so much time. That would be too long to assimilate anything. Maybe, is it okay if I take another 15 to 20 minutes?
Yeah, no problem.
Okay. I mean, I just don't want to sort of, go on forever because this is, if it's not interesting. Okay. So where we stand here is we are now ready with common source of randomness at all the nodes. And then we are now interested in extracting secret bits out of them. Okay. So what is next? Now, at this point in time, the samples are discrete. Now, if the tree nodes wish to, they can as well quantize these into binary digits and then go ahead with usage of secret key. But then, given that it's a noisy setup and there is asymmetry in the noise, especially with one of the nodes who could not see the channels explicitly, then using these exact samples for digitization is not a good idea. That would in turn sort of increase the mismatch rate in the secret bits that are generated among the nodes, right? So what we want to do now is we want to further quantize these samples into multiple levels, but then the number of levels that we would now use has to be carefully chosen. So the simplest that I could do is, I can just partition this into two groups so that I'm going to decide that I'm only going to extract one bit out of a sample. Right? To generalize that, what we can do is we can say that I'm interested in extracting B bits per sample, that's B. So what it means is in the dynamic range that I have of these QAM symbols, I need to identify 2 power B such regions, okay? And once I have these 2 power B regions, then what it means is we also need to decide how to really draw the boundaries here. And then going by the basics of guard bands that was discussed in the preliminary part of the 2-user key generation, these boundaries are not just thin lines. These are thick lines which are called guard bands because we want to really arrest some of the errors that would creep in from one region to another, right? So in order to convert these samples into bits, we need to decide on the value of B, which we are going to call it as a quantizer. And then the definition of a quantizer is I'm going to say, where am I going to draw these boundaries and how thick are these boundaries, okay? And once I decide that, what I can do is I can go ahead with another level of quantization, which is the samples are already discrete. I'm again going to put them into 2 power B bins, okay? Because the current levels are too large to really sustain any errors, right? And then what I'm going to do is, if in the process of this quantization, if the samples lie in any of those guard bands, I'm going to discard them. Very similar to the approach in the case of 2-user key generation. And then the samples that are outside the guard band, we are going to say that, well, it is in consensus. So the consensus algorithm in the case of 3 users is very similar. So what they do is when they quantize their samples, they're either going to end up with a legitimate level, which is given by, let's say, AJ for some J running index. And then if the sample lies inside the guard band, I'm going to call it an X, and then I'm going to discard it, right? So each one of these nodes, they apply the same procedure because they have decided upon a quantizer that is mutually agreed. And then what they do is they broadcast those index values that don't fall as X, okay? They look at their samples one by one, which is basically the underlying assumption is that the protocol has already been implemented over a number of coherence blocks, and they already have a lot of they already have a lot of samples that are discrete. And then when they apply this quantization on each one of these samples, and they are going to share the index values of samples that are out of the guard band, and then each one of them is going to do this, and then they finally agree upon common set of indices, and then on those indices they would then try to extract the secret key. Now the question at hand is, how do we really design this quantizer? In other words, all that I need to do is somehow need to decide on where to put those boundaries and what should be the thickness of those boundaries, right? So in order to put it formally, I'm going to call them as a part of design criteria. What are these? Number one, I want to maximize my symbol rate. What it means is we would like to have as many samples as possible lying outside the guard band. Otherwise, they would not be useful for key generation. Point number two is, once I generate these bits out of this quantization, I need to make sure that the entropy of these bit sequence is maximized, right? So you're going to end up with a bit sequence, and then I need to see some randomness properties in these bits. It's like, I don't want to see an all ones, or I don't want to see an all zeros, right? That would be of no use, right? So they have to have maximum entropy. right? And then the maximum entropy that they can have is, the B times the total length of it. And that's one, entropy is one of the criteria. And the third criteria is, once I design this quantizer, it should be such that, when I compute the mismatch in terms of the pairwise differences in the bit locations, that has to be minimized. Or let's say we would need to upper bound this by some small negligible number, right? So I need to really now take a look at how to design my quantizer in order to achieve these criteria listed here, right? But how to do this? It's actually a very Herculean task. The reason is, we are looking at random variables, 3 of them that are correlated, right? And then each one of these nodes is going to come up with their bands for quantization, and there are as many underlying variables for optimization, correct? And then if we need to really jointly optimize all these bands, that's rather complex, right? So that's not feasible at this point in time. So what we do is, we are going to simplify the problem and then relax a bit with an affordable suboptimality, right? What we'll do is, we are not going to look at all these 3 random variables as a 3-dimensional distribution. We are going to focus only on the worst pair, which is the CSR sample at the node 2 and node 3. Why am I calling them worst pair? If you see the noise, relative noise between these 2 nodes, it's actually the cumulative effect of the reciprocal noise which occurs in this link. And when it then gets forwarded to node 3, this is the decoding error, right? So in some sense, it's a cascaded effect of the decoding error as well as the estimation error would be the relative noise between the 2. And then what we are going to see is, for the time being, I'm not going to worry about the facilitator. But what I'm going to do is, I'm going to look at the samples between node 2 and node 3, and then I'm going to forcefully look at it as a 2-user problem, because I'm only trying to simplify it, because my optimization problem is getting out of hands. Okay, so then we are going to ask the same question, but just the point is that all those criteria that we initially applied on the 3 keys, K1, K2, K3, we are only going to apply on the 2 keys between node 2 and node 3. Okay, now fine, we are going to work on an optimization problem here, which means I need to design these bands, or this position and widths of these bands that are here. Now, in order to figure out what is the right choice, we are going to make an assumption that I have the joint distribution of these random variables. Okay, so somebody gives me, let's say a genie gives me the PDF of this joint random variables, and if I have these joint random variables, how will I really design these bands? Okay, in order to study that, here is a picture. What I'm going to look at is, this is basically on the x-axis. You can think of this as 4 levels as an example for one of the users. On the y-axis, these are the 4 levels of the other user, and basically these are the guard bands, right? There are 4 levels. That means there are 3 guard bands. If the samples lie anywhere in between, they would be discarded. Sample lying anywhere here, discarded, and so on, right? Now, the 2-dimensional distribution would sit on the 3rd dimension. So when you're looking at it from a top view, you can imagine that the PDF is actually sort of protruded towards your side. Okay, and now what I'm going to do is, as an optimization problem, I'm going to vary these guard bands to the left and right, or expand and so on, in order to ensure that some of my all the criteria that I mentioned is optimized. But then how do we really connect the criteria and the information on the joint distribution? We can do that. What we can do is, the first criteria point was that we had to really maximize the symbol rate, right? Now, if you look at it in this 3-dimension, what does this mean? Now, you have a joint PDF sitting on top of it in the 3rd dimension. Now, if you compute the mass points in the areas marked in X, and then if you sum them up, that basically gives you the probability that the samples are in consensus, because we are discarding those samples that are lying in these guard bands as well as these guard bands. So all that you don't need to do is, if you know a given set of boundaries, we can compute these probability mass values, and then this at least gives us some metric to maximize my symbol rate. Okay, what else? I also had to maximize my entropy. And then what does entropy mean in terms of joint distribution? We actually wanted to maximize the conditional entropy because we want to maximize the entropy of those sequences that are already in consensus, right? And then, you could fall back on the basics of probability, and then you can write down the conditional entropy as this form, whereas a given probability value here, it's nothing but you basically add up the mass values on given here in the red boxes, and then you divide them by sum of all the mass values in the cross. Okay, that would in turn give you the probability value of a conditional probability value of a given point which is out of consensus. Now this is only value for one sample. I can actually compute the same for all the other samples, and that would give rise to all these GJs, and once I have these GJs, I can compute my conditional entropy. Okay, so that means what we now have a very good hold on how to really maximize the conditional entropy using the joint distribution. And finally, we are also interested in the mismatch rate. And what it means is, again, look at the same picture. Now, I'm going to identify those areas that I would like to minimize. Okay, essentially, what are these? These are these cross areas because, for example, if you look at this area, this is a region where, this node quantizes to level A1, whereas this node also quantizes to level A1. But if you look at all the other points, these are all they're all in consensus, but they all have mismatches. I don't want to really entertain these. So in the end, when I vary these bands, I need to make sure that the area, the sum of the mass points coming out of these red cross values are minimized, or it is upper bounded by some negligible number. Okay, so with that connection between the design criteria as well as the joint distribution, we can actually formulate an optimization problem with a number of constraints. That is what is shown here. Now, solving this optimization problem is again a Herculean task, although this is much simplified version by considering 2 users. Now, what we have done is we have rather proposed an iterative algorithm in order to solve this. Okay, so there are no guarantees on optimality, but we have sort of tried to ensure that the algorithm quickly gives us some reasonable bands so that we could place them to quantize it. Okay, important blocks are going to be the error block. This is the block which will take care of the mismatch rate. The entropy block will take care of the entropy and corresponding, and so on and so forth. Right. So the first block is usually called as the initialization block. This is basically to ensure that all the samples have maximum entropy. That's basically redundant in the case of our protocol because our initial constellation itself was chosen in such a way that the samples were uniformly distributed. Right? But what happens is the error block, it doesn't worry about the entropy because we have sort of put them into 2 different parts. I'm going to focus on error, you focus on entropy, and then they iterate among themselves until the criterion is met, right? That's basically the idea. So although the error block, if you look at it, it needs to really minimize all these sample values in all the crosses, which also included a lot of these areas. But then, in order to locally minimize for a given band, we have only looked at the immediate neighbors. Okay. So for example, if I'm looking at this particular guard band, what I will try to do is I'm going to expand this guard band until my area in this region and this region are reduced to a certain level. Okay. Then once I'm satisfied here, I'm going to move locally to the next band and I'm going to increase the guard band here and until, these 2 values come down. And likewise, each one of these bands are enlarged. And once that is done, the ball is passed on to the entropy block. And what the entropy block does, it only focuses on maximizing the entropy, and therefore it doesn't really worry about the cross terms in the red. All that it worries about is that, all that I'm going to make is I'm going to ensure that the mass value in this blue color value is going to be very close to 1 over 2 power b, because you have 2 power b levels, and then I need to make sure that I need to maximize the entropy. Therefore, this block, it doesn't try to expand the guard bands. It only tries to translate it either to the left or the right in such a way that the mass value that is appearing here is going to be almost 1 by 2 power b. Okay, this does this job locally. Likewise, the next band, will also move its band to the left or right to ensure that this is approximately 1 by 2 power b, and so on and so forth. But now, as you can see, this is very heuristic, right? Because when each one of them does their job, maybe the previous value may get perturbed, but then there's something that we have to live with it if we are looking at local optimization. Okay, and then the entropy block does this and then passes the ball to the error block. Again, that expands the guard band, gives it. They keep iterating until a point that they are satisfied that the bound on the error is met. Okay, and once the bound on the error is met, what happens is in the end, if you look at these particular regions in the green, it may so happen that because of the local optimization, all these values may not be really identical. Okay, so in order to sort of refine everything, what we can do is we can identify the smallest number in this non-zero number, and then once we identify the smallest number, we can change or rather expand the inner bands of these side. Okay, how can I reduce this number? I can actually expand this side of the band and this side of the band internally, okay, in such a way that this number will be equal to this number, right? Now, in the process is such that I'm also increasing the band, I'm sort of only expanding the inner walls, and as a result, this may result in further reduction in the mismatch rate, but then we had to accommodate in order to ensure that all these values are identical. And if all of them are identical and the rest of the values are all negligible, then we can easily show that the entropy of the resultant key could be maximized because of these boundaries. Okay, so with this algorithm, what we refer to as EMEM is entropy maximization and error minimization. We have tried this on two-user key generation to start with, and this is basically the result that we get in terms of the bits per second secrecy rate. If you choose 2 levels, you would get this 4 levels and 8 levels and so on. Okay, and then we were also able to sort of compare the guarantees in terms of entropy, because that is one of the key features of this. And we could actually compare this with schemes which would do optimization by just making use of marginal distributions. Because if each of these nodes would like to design their bands locally just by looking at the marginal distribution, that would be suboptimal, right? Because in order to maximize the conditional entropy, we need information on the joint distribution of these 2 random variables, right? So evidently, because of those, we end up promising, we end up getting maximum bits as what promised. Okay, and we have indeed used some of these ideas for the GSK protocol in place. Basically, going back, we already had these discrete constellations, discrete size constellation with them. They applied this EMEM algorithm on top of these samples, and then we were able to extract the bits with maximizing the entropy as well as minimizing the rate. Okay, so I'm not going to get into the details of this for the benefit of time. And basically what it means is we have sort of figured out how to really obtain these boundaries through an optimization problem which is matched to the underlying structure of the common source of randomness, which are essentially discrete. Okay, so to summarize, what have we done so far is that the first phase was distribution of common randomness, and the second phase was really about synthesizing secret bits out of those randomness. We have looked at how to really design them jointly, and whatever we could get was those results. Okay, and there are a number of opportunities for enhancements. There are opportunities where we could potentially make use of coding theory ideas in order to further mismatch in order to further reduce the mismatch between the keys among the nodes. But again, I'm not going to talk about each one of them. Initially, I thought I would throw some light on it, but for the time being, I'll refrain from doing so. Okay, so that basically the ideas here involve how to use traditional LDPC codes to help these nodes to further reduce the bit mismatches. Okay, I'm going to skip that in the benefit of time. Okay, so overall, the takeaway from this particular talk is that decentralized setting is important because this is reminiscent of the distributed ledger case. wherein we don't want to really rely on one node to take up all the responsibilities. As I said, if that turns out to be rogue, then we end up in some issues, right? So that's the reason to look at the decentralized setting. We looked at the specific case of 3-node. Although the setup is very simple, we have seen the challenges in really sharing the common randomness and then synthesizing key out of it, right? And we have looked at the practical aspects of it. We have also looked at the confidentiality aspects of it as well, right? We are excited about many things here because there is definitely room for optimization at different levels. And as Lalita asked in the beginning of the talk, sometime in the middle, we have little idea as in really how to scale this up. When we scale this up to arbitrary number of users, the first thing we need to do is enforce a given topology on them, whether it's a complete graph or whether it's a sparse graph, who is connected to whom, and so on and so forth. And it's a function of that. Then we need to really think about how to share the common randomness, and then how to achieve the consensus algorithm. So we think that it is extremely closely tied with the topology in the case of multi-user network. Okay, so just to conclude, other than getting into the details of optimization and then figuring out the protocol correctness and then the optimization results, we at IIT Delhi, we are also involved in sort of developing these ideas into prototypes as test beds. And in fact, this particular project that we're working on, this is one of the deliverables to Department of Telecommunications as part of the 5G project. So we have some demonstrations ready with us, wherein we have used these algorithms to implement and show that key exchange is possible inside the lab environment as well as outside. However, we are able to implement the 3-node network, which is something that we would need to do once the pandemic subsides. Okay, and with that, I will conclude my talk. Hopefully, this has given you some ideas related to key generation, especially with respect to physical layer ideas and its generalization to group key generation. So thank you very much, and thanks for your patience. Back to the organizers.
Thank you, Harshan. So I guess we have some time for questions.
Yeah.
I request the participants to, if you want to ask a question directly, you can raise your hand, you can click button, we will unmute you so that you can directly interact with the speaker. Or you can type in your question in the chat window and we can relay that to the speaker. Okay, so please feel free to ask questions. So in the meantime, if Sad or Shashank or Tarita, you have any questions?
Yeah, so one question, Harshan. So the optimization algorithm that you run, that's done beforehand, right? It is not done on the fly by any of those guys.
Correct. So that's a good question. So we need to develop statistics. We need to develop measurements and then build a model out of it, and then this has to be run offline. And once the bands are decided, they would then use it in the real time.
So just curious. I mean, you mentioned that you've already done some experiments with hardware. So are all the assumptions regarding statistical independence of the channel coefficients and all of that, do they really hold in the real world? Okay, so we can definitely vouch for a few things based on our experiments. As far as reciprocity property is considered in terms of observing correlated random variables, that is indeed true, because we are able to get keys of non-zero key rate. Okay, and now coming back to the question on analyzing the confidentiality of it. Now, what we have observed is we have empirically sort of tried to figure out the statistical independence between the observations made at the eavesdropper and the samples that are used for key generation. So we did observe some amount of independent property between the two.
But then what we have not yet done is we have not used any statistical method to sort of understand their Kullback-Leibler divergence or numerically compute the mutual information between the two to have any evidence. We haven't done that yet because really focused on the confidentiality part.
Exactly.
But that would be the way forward.
Yeah. So I guess, I mean, of course, it's computationally intensive, but many results in the, I mean, many works in the secret key generation literature typically do some post-processing by using some kind of a hash function or some privacy amplification. So are you also exploring things of that nature?
No, that's only going to, yeah, definitely it is one of the overall end-to-end key generation methodology. This is something that is even before that. So all hashing and other things could follow these blocks.
Harshan, so I have one question. So I don't know, maybe something I missed. So when you are doing this physical layer network coding, so you said that it would cause information leakage, right?
Yeah. Yes,
is it a easy thing to see? Why that?
Yeah, so yeah, that is for somebody who is, I would say so. So let me try to go back to the expression, which, in fact, if not the expression, we can as well go to this place. Okay, so now either we could look at the mutual information expression here, okay, or we could try to visualize the constellation diagrams that we see. Right. So, this is one random variable, this is the random variable of interest to extract the key. Whereas what we have here is another random variable. Okay. So you could think of this as, let's say, the typical AWGN noise, because this is statistically independent of this. You could think of this as y is equal to x plus n, and you could think of this as x. Okay. So what it means is the mutual information between y and x. And we can show that this is non-zero.
Okay,
That's one.
right.
That's one way to look at it in terms of mutual information. The other way is to really look at the constellation diagram and see that when you add up 4 points and 4 points, we don't really end up with 16 points of uniform distribution.
Right. Yeah.
So, any questions from the participants? Please feel free to interact. So, Lalita, you have a question?
No. I mean, I didn't.
Okay. So, Harshan, maybe I can take you back to my previous question. So, maybe a slight application of that. Let's just consider this 2-user case, and then you have this source of randomness, which is your channel, let's say H12. And if you think about it, this H12 is maybe a Gaussian random variable. So potentially theoretically, it has infinite number of bits contained in it.
In both that. Yeah.
Yeah. So when you're quantizing using the scheme that you showed in the slides, you are getting 4 bits out of it. And I think you got 4 bits out of it. You wanted to use 16 quant for, right? So I was just thinking if there's any other hack or trick through which you can extract more information or more randomness from the single complex random number. For example, let's say you do your scheme once, you get 2 bits out, and then I transmit maybe an offset version of H12. I add a constant, predetermined constant to H12, and then I transmit, or something like that, which will get more bits out of the same source of physical randomness.
Okay. So yeah. So there are a number of inhibitors to this. Okay. So definitely this is a function of signal to noise ratio. So if the noise levels are too low, then essentially we can actually enlarge the dynamic range, and then we could be more greedy in extracting more bits per sample. So that's definitely viable. But then I guess your question is, for a given signal to noise ratio, what can we do more than what we have done already, right? So any amount of additional side information that you want to convey to your legitimate nodes must somehow also ensure confidentiality, because the eavesdropper is listening to all the conversation. This is so we haven't really thought about how to sort of come up with enhancements to the scheme in order to further increase the number of bits per sample. However, something that I just skimmed through in the last section of this presentation was that, if you look at this 3-node network, all of them have 2 channels, in fact, H12 as well as H13. Okay. Because both H12 and H13 are coming to them for free just because of the underlying protocol. But they end up using only H12 and not H13 because of the mutual information expression. Using both would lose out on the confidentiality. So one way to really increase the key rate is to be be extremely opportunistic. What we do is you be vigilant and open-minded in terms of looking who is out of consensus and so on. On a given coherence block, if H12 is out of consensus, you use H12. On the next block, if H13 is out and maybe H12 is not, then you just grab H13, right? And then otherwise, if we are very rigid about only making use of H12 as my common source of randomness, maybe there are instances where H13 is amenable to key generation, but I'm just not using them because of my rigidity. Right. So again, I know that I'm not answering your question, because all that I'm telling you is that there are other ways in which you can really increase the number of bits extracted per coherence block. But if we are adamant on, with only H12, what can I do more in order to really get more bits out of it, right? So one thing I told was that we have to unfold it. Okay, so you get in-phase and quadrature component, and then we are going to apply quantization on each of these quadrature and in-phase. So we would get the sum of the 2 bits from both of them, provided both of them are in consensus. If they are not, because they are statistically dependent, the in-phase component may be in consensus, but the quadrature may not be. So because of that independence, it boils down to just one of the real symbols.
Okay, thank you, Harshan. So I guess there is a raised hand in the audience. So Lalita, will you be able to unmute the participant, Sultan Alam?
I am trying to, but I'm not able to, I guess. Yeah, I'll just check. So I have asked them in chat. I'm not somehow able to unmute, I guess. Yeah. So there's I think a question in the chat. So yeah, so he wants to ask about the mutual information term, but I'm not sure which one. So okay.
So we encountered this at just only one place, I believe, at least in terms of the expression. Yeah, so I would like to know what exactly is the point.
Please type in your questions so that we can ask the speaker. So right now I don't see. Okay, so we'll just wait. So Harshan, I had one more question too. So I think this algorithm can be extended to lattices based constellations, and I mean.
Yeah. So, yeah, that's a great question. So, in fact, whatever we have is a very primitive version of it, which is just in 2 dimensions. Now, I mean, even if we work with lattices, these are basically nested, right? Because we finally want to take up only finite points. Now, we could look at using multidimensional lattice, provided we work on the basis of a vector. So what we need to do is, here in a given coherence block, we are only looking at one complex number at a time. But then perhaps we need to run this algorithm for let's say n such consecutive coherence blocks. And now imagine, for example, related to the question asked by Shashank, underlying correlation in the wireless channel between the coherence blocks, then maybe there is we are forced to view these vectors, view them as vectors instead of scalars, in which case we could directly apply a vector quantization onto the points in a multidimensional lattice, and then work on the lattice points as vectors rather than complex numbers. That's definitely possible. That's the way forward.
Okay, so
Then
yes.
Yeah.
Go ahead. Right.
No, I was just trying to add another point that if we do so, there was a related question by Shashank that how can we really minimize the error at the time of broadcast? And perhaps that is where lattices could help, because as we increase the dimension of the lattice, and that means when we gather number of consecutive samples, maybe there is a scope for us to look for good lattices that have large minimum distance, right? So those with good Varana region could really be helpful here. That's one way to really reduce the error.
Yeah, so I think the question by Sultan Alam is that instead of can you use mutual information terms?
Yeah, so now we have to think about it, because entropy comes in naturally, because the reason we looked at entropy was that once the keys are derived, they need to look sufficiently random. Now, if we want to think about mutual information, I just need to wonder what would be the other random variable for mutual information. Maybe there's one way to do it. What we could do is, in order to study the effect to which the correlation among the random variables is maximized, we could try to maximize the mutual information between pairs of random variables observed at all the nodes. Okay, and this will not be helpful at the time of quantization, but I think this will be helpful in designing the protocol for sharing the common source of randomness, if I'm really thinking along the lines of the audience.